Hello, this is a video which is me going through an Edexcel GCSE Computer Science sample paper. Actually, it's not a real exam paper. This was produced by the exam board as an example, and so there aren't any grade boundaries, unfortunately, but it is a fair, realistic example of paper 1. So the theory paper out of the two, I've got a walkthrough on paper 2 as well, the more practical version. I'm going to be going through every question without having seen the mark scheme yet. I'll check the mark scheme before I upload it, just to give you my thoughts and hopefully go through things like exam technique and misconceptions and things like this. So this paper is, like I said, the theory paper is out of 75 marks, and the time you have, unless you've got extra time, is an hour and a half, which means you have an extra 15 minutes to check it if you are doing a minute a mark. And for theory papers like this, the general aim and the general design of the paper is to spend about a minute per mark available. That will help you guide your time. Now, just a couple of key points which you don't want to, forget, especially if it's your first exam. Black ink only bring black pens in. Bring a pencil and a rubber in as well, because certain questions you'll have to rub stuff out if you make a mistake and it'll be quite difficult otherwise. No calculators, don't bother trying to take one in. For maths is not hard, but usually Edexcel don't even ask you to actually give final answers. Often they ask you to give that in expressions, as we'll look at. And the advice at the bottom is sage advice. Read each question carefully. Try and answer every question. I haven't examined GCSE before. It was honestly eye-opening to me the first time I did it, how many questions get left blank. Don't be one of those people. Guess if you're not sure. And finally, check your answers if you have time at the end is good advice. As we'll see, this paper is really broad. There's loads in it. Make sure you've learnt the content and revised the content before you go into either a mock or real exam. I've got a playlist which covers all of the content in loads of videos for Edexcel Paper 1. That should cover all the content you need to be able to do this paper and do it well. You can find the playlist in the description or on my channel page. So let's start with the first set of questions then. And interestingly, well, I think it's interesting as a teacher, Edexcel group these by topic. So each question will be based on one of the 5 topics eligible in this paper. The order will be different each time, I suspect, but at least once you start a question, you know, or at least it narrows the pool of possible answers. If you know that specification document off by heart, pretty much, it will help narrow down the possible answers if you're not sure. It will make guesses more accurate, I suppose. Now, as we'll see later, there will be a question on almost programming, not practical programming, but from a theory perspective. So bear in mind, it's not just for kind of natural theory, quote unquote, topics. It's a bit more than that. Starting with data, so data rep essentially. Now, first of all, we've got to identify the smallest unit of measurement. So bit, byte, kibby, byte, nibble. A bit is our smallest unit in binary. A byte is 8 bits. A kibby byte is 1024 times 8 bits. And a nibble is 4 bits. A bit is just 0 or 1. Now we need to identify the maximum number of values that can be represented with 5 bits. Now this crops up a lot in data rep. So it's just an important, not even really a formula to know. To work out the number of values given by a binary number, you always do 2 to the power how many bits you have. And in this case, we've got 5 bits, so 2 to the power 5, which is 32. Now, a car park uses a number plate recognition system. Identify the reason why an unsigned integer should be used to record the number of cars entering the car park rather than a signed integer. So unsigned integers are more accurate is option A. Unsigned integers cannot have overflow errors, which is not true, so I'm going to rub that one out straight away. Unsigned integers store more positive values, and unsigned integers do not use a parity bit. Well, that's not relevant. I'm not sure what topic it is, but not relevant at all. Parity bit is about checking for errors during transmission. So what it's talking about here is, obviously in decimal, in denary, we've got positive numbers and we've got negative numbers. Well, we do that in binary too. So for instance, 2 in binary would be 1, 0. Sorry, positive 2 in binary would be 1, 0. Well, if I was to do negative 2 in binary, we do this in 2's complement. And in 2's complement, the far left digit is always 1 if it's a negative number. Okay, so 2 in binary would actually be 1, 0 after the sign bit, giving us 1, 1, 0. Now, if I zoom in, the reason for this is effectively that far left column is representing the negative value of that place value. This is our 1's column, our 2's column, then our negative 4's column. And so really with 110 in 2's complement, I'm saying I've got negative 4 plus 2, which is minus 2, plus nothing. So plus 2 is 10, negative 2 is 110. And we can spot the difference straight away, right? The negative version has got an extra bit. So therefore, it's really the converse of part C. The fact that unsigned integers store more positive values, because we're having to use a bit as a signed bit, it limits the number of possible values because I'm using that one up. And so therefore unsigned gives us a bigger range of positive values. Now for a car park, the number of cars entering is never going to be negative. So why waste that signed bit on something which will never be used? So therefore the answer is C. Accuracy is not really relevant when we're talking about integer parts of numbers. Okay, and for II, we've got our first free marker, which is always nice to get going, get some marks properly on the board. So the system stores images of car number plates, construct an expression. This is what I meant a bit earlier when I said you don't actually often have to carry out calculation. We just write down the equation. To show how many bytes there are in 6 tebibytes. So for tebibyte, T-I-B, it sounds silly in my opinion, but there we go. So what I'd be doing at this point, you might not have it straight to hand straight away. I would personally write out the sequence of our units, right? So we've got a bit at the smallest, then you've got a nibble which will skip, then you've got a byte, then you've got a kibibyte, then you've got a mebibyte, then you've got a gigabyte, and then finally you've got a tebibyte. Now importantly, and you could highlight the question if you've got highlighter too, it's asking for bytes, not bits. So I wrote that first bit out unnecessarily. We don't care about bits this time. So effectively, how are we getting from bytes to tebibytes? Well, we're timesing by 1024, which is what each of these is of the previous term. How many times are we doing this? Well, we're doing it 1, 2, 3, 4 times. So therefore, it's going to be 1024 to the power of 4. And how many tebibytes do I have? Well, in this particular case, I've got 6. So I'm just going to multiply this expression by 6. Unless you're crazy, you would not then try and work this one out. You'd leave it as it is. If it says construct an expression, it's left as it is. Now, I've definitely found my own students occasionally getting mixed up between, well, do you times or do you divide? You know, here I'm timesing by 1024 to the power 4. Well, you know to times because if you're going from a unit like tebibytes, which is massive, if you buy a hard drive nowadays, they're usually a few tebibytes, or terabytes as it usually is marketed. That's a massive amount of data. And so if you're going from a big unit to a small unit, you're timesing. If you're going from a small unit to a big unit, you're dividing. Okay, for part D, identify the 4-bit binary addition that will result in an overflow error. Now, I mentioned overflow errors in the previous question. I very quickly crossed it out. Well, here we've got 8 numbers, which we have to assume are unsigned. And so even if you weren't sure about CI, if you get to this question, you might realize that actually it can't be CIB because here it's contradicting that question effectively, right? So an overflow error is where we carry beyond the number of bits allocated. So we've only got space for 4 bits. If our result is bigger than 4 bits, that's an overflow error. To be honest, it's only 1 mark here. You could sit and do every binary addition here. I might do one just to show you how this works, but what I'd be looking for if I was doing it, which I am doing it now, be looking for the first digit of each number. Well, if we've got 1 plus 1 here, regardless of the rest of the number, that's going to be 0, carry a 1. And so immediately that's going to overflow beyond the 4 bits. And so that one must result in an overflow. We might want to look at some of the other ones just to satisfy that and just double check. The next one, which looks quite likely, is, I was going to say D looks quite likely, but actually we can see we've got 3 ones here, which are cancelled out by the zeros, then this 0 is cancelled out by this one. So that won't be overflow, it'll just be 4 ones. But C, you might be looking at thinking, well, actually no, because C is just going to be 1, 1, 1, 0. And you might look at B and be unsure. So let's try B just to demonstrate this. 0, 0, 1, 1, 1, 0, 0, 1. Binary addition is the same as normal addition, just we carry if we've got two 1s. So 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. 1 on its own is just 1, and then 1 on its own is just 1. So here we had a few carries, but they don't carry beyond the 4th bit, and so it doesn't result in an overflow error. Now time for some conversions. So we've got to give the 8-bit binary representation of the denary number 82. And 2 marks here is a little bit generous, to be honest. These are often only 1 mark, I have to say. So make sure you go in with your conversions just second nature. Right, so what I would do personally is always start drawing a table, the place value table for binary, starting with 1 on the right hand side, 1, 2, 4, 8, 16, 32, just doubling each time. And I can stop at 64 here because the next one is 128. And although, I almost made a mistake here. What I was going to say was, we can stop at 64 because the next number, 128, is bigger than 82 and so won't be used. However, I realised that actually, if it's asking for 8 bits, I've still got to include 8 digits, even if I have a far left 0. If it's asking for 8 bits, I've got to give it 8 bits. And without it, I'd only have 7. Okay, that was a good example of where you can make a mistake with these questions. Right, so what you do is you start, once you have your table, left to right. As I say, 128 doesn't go into 82, but 64 goes in one time with a remainder of 18. 32 doesn't go into 18. 16 does go into 18 with a remainder of 2. And so 2 goes into 2 with a remainder 0, and that's us. So you might want to write out your answer so the examiner doesn't have to, look too carefully. Our answer should be 0, 1, 0, 1, 0, 0, 1, 0. If it's asking for 8 bits, make sure you give it 8 bits no matter what. We're now doing a conversion to hexadecimal from binary, and despite having 8 bits given to us here, the key with these conversions to hexadecimal is to always isolate the nibbles and deal with them separately. Okay, so it'll be quicker if we separate it. So the first step is to convert each nibble to denary, and then you convert each nibble to hex after that point. So 0, 0, 1, 1, first of all, what is this going to be in denary? Well, you could do the table really quickly. I tend to find that over time you can do this in your head quite easily, but you want to be cautious, obviously. So 2 plus 1 is 3. So let's do it on this side. This is 3. And 1, 1, 0, 1, 2, 4, 8. 8 plus 4 is 12, plus 1 is 13. Another job is to convert each of these two to hexadecimal. Well, digits 0 to 9 in hexadecimal are the same as in denary, and so 3 is just 3 in hexadecimal. But 13 is not 13 because it is 2 digits. In hex, A is 10 and F is 15. That's all I would bother learning as you go into the exam, because B is 11, C is 12, and therefore D is going to be 13. So 13 is D, and to be honest, we don't really want to write it like this because what we need to do at the end is put them together. So the actual answer should be 3D. For II, we have our first proper written question. So we've got to explain why hexadecimal notation is used for 2 marks. Note how it says explain. This could equally be a state question. A state question, you're just giving reasons, but explain, you're saying why something is the case. So really, what makes hexadecimal useful for this benefit? Well, first point I'd make here is, as evidenced by the previous question, 1 hexadecimal digit equals 4 binary digits. That's really the why. And so therefore we can shorten long binary numbers when using hexadecimal. So I've changed colours here because, when I'm answering questions, I tend to try and think, how is it getting marked? What are the 2 separate points which are going to get me 2 marks here? To be honest, I would say this possibly isn't 2 marks. I would play it safe and add a 3rd point, because I haven't really said why this is good. Why does this make it useful? And we can maybe be even more clear about this if you had time in the exam. So this makes it more readable. And I might just say for us here, because a common mistake is people assume hexadecimal is used in a computer as some kind of compression mechanism, but it's not. It's only used for humans. Everything's in binary in the computer. And maybe we could say, and fewer mistakes might get made using it. The point being, if you've got a very long binary number, it kind of blurs together and doesn't stick in your mind, whereas short hexadecimal is a bit better. We now have an analog to digital converter being used to change the sounds received by a microphone into a form that can be processed by a computer. Complete the diagram to show a sample interval and label both axes. Okay, for 3 marks, blimey. Okay, so fine. I guess we're getting a mark per axis and for a sample interval. Well, let's do the axes first of all. So this is showing how a wave progresses over time. And so the x-axis is time. So let's do that. And the unit is seconds. So lowercase s. I was always taught, I don't know if it was GCSE or A-level, to do a slash for my units, but you could do it as an s in brackets, I suppose. And now the y-axis, so the height of your wave, well, the height is your amplitude, but the formal word is displacement, because the amplitude is technically, again, I'm going back to A-level physics here a little bit, it's technically the height of your wave, right? And the unit for distance in physics is always meters. Despite waves being tiny, in most cases, distance is usually meters, which in sound is also like, for a sound wave, the height corresponds to how loud it is. If I start screaming, the sound wave will be much bigger. So this would equally be kind of how loud it is, the unit being decibels, or lowercase d actually, decibels like this. But I think displacement is the technical correct answer. Now, in terms of sample interval, well, let's draw it taking a sample like this. A sample is measuring the height of your wave. If you had a ruler, you might do this a little bit more accurately. We can try and do several samples maybe to demonstrate this. They should all be roughly the same distance apart on the x-axis, because that's what the sample interval is. The sample intervals are the gaps between each sample. So we could say this is the sample interval. The point of the samples is they're taken at regular intervals, and so the gaps should be the same. Now for H, and we're probably coming to the end of this question. Yes, we are, so no more data rep. It's generally quite a nice introduction if you get it up first. So an image uses a 12-bit color depth. It is 64 pixels wide and 48 pixels high. Construct an expression again to calculate the file size of this image in megabytes. And it's worth 4 marks here, so we've got a bit, if it's worth 4 marks, make sure your working out is nice and neat, especially if you know this perfectly. If you weren't sure how to do this, you can probably pick up quite a few marks just by, linking the numbers together, and just as a guess maybe. But we want to be able to do this properly. So, first of all, we want to work out the resolution of our image, so how many pixels we have. And we do this just by multiplying 64 by 48, which we're not actually going to do because that would waste our time. And the color depth, it tells us, is 12 bits. So the color depth is 12 bits already. Sometimes, I always drill my pupils to be really careful about color depth, because often people assume it's the number of colors, and so they make mistakes. If it's in terms of bits, you leave it as it is. If it said 12 colors, that's another question. You've got to do, 2 to the power something equals 12. So x would be 4 in this case, because 4 bits would make it bigger than 12. Anyway, you might recognize that, you might not, but 12 bits is our color depth. And now, to get a file size in bits, I just multiply these together. So I'll write that down, file size. Be really clear, this isn't my final answer, it's just in terms of bits. I would do 64 times 48 times 12. Okay, well, how do I get from bits to megabytes? So we've got bits, oops, not uppercase B. I've got bits, then I've got bytes, then I've got kilobytes, then I've got megabytes. Now I was saying earlier, if we're going from a small unit to a big unit, which is what we're doing here, we're going from bits to megabytes, we're going to divide. So we're going times 8 at this point, but really, I should say we're dividing by 8 at this point, because we're going from small to big. Then we're dividing by 1024, then we're dividing by 1024. So really, I can just stick this in a big expression and put it as my final answer. So it's going to be 64 times 48 times 12 divided by 8, and then to do divided by 1024 squared, I could just do times 1024 squared. That's the same as dividing both individually. And then I would say this is file size in megabytes. We're now on the second part of this paper, which is on the topic of networks, which is quite concise as a topic, but it's got lots within it. And we start with a hotel chain having hotels in several countries and a head office in England. State the type of network needed to connect these hotels to the head office. Well, there are quite a few different types of networks. To know which type it refers to, really looking at the spec and knowing what exactly is on the course. Well, the two types of network on the course are LANs and WANs. A LAN is a local area network, a WAN is a wide area network. Well, what is this going to be? Several countries and in England too. Well, it can't be a local area network, which is usually just one building or a couple of buildings. It must be a wide area network, which is a WAN. The only other part I could see people getting mixed up with are topologies, which is coming next actually. It would say topology in the question, or it would make obvious that it's a topology. The arrangement of the network, which is what a topology is not clear at all from 2A. So it's got to be either a WAN or a LAN. So now we've got to draw lines between these boxes to show a fully connected mesh topology. So in a mesh topology, every device is connected to every other device. You can have partial mesh topologies, which are not completely connected up, but a fully connected one has got to connect to every other device. So let me concentrate while I do this. I think that is it. Not particularly neat, but that should be every device connected to every other device. Right, now part C, routers send packets that contain data around the internet. State two other items found in a packet. So the idea is we don't just send messages or web pages or files in one go. They're broken into packets. So there are three parts to a packet. We've got our actual data in the middle, which has been taken in the question. We also have a header, which I probably can't fit in properly. A header at the top. The names vary a little bit for what this is. And we also have a trailer that's barely legible. There we go, trailer, kind of. Right, let's pretend I didn't draw that. The header and trailer could be the same thing. It doesn't matter for our purposes, but contain information about that data. So one important thing which stands out to me is the sequence number or the packet number. So this is telling us what packet it is within that wider bit of data being sent. So it might say, okay, this is packet number 17 of 205, say, right? And that's needed so we can, at the end, when it's all received, reassemble it to be the original file that was being sent. Without knowing which packet it was, you'd have to rely on it being the order of arrival, which can vary quite a lot when it's being sent down different routes across the internet. So sequence number is really important. Another important thing is the destination IP address. The source IP address is there too, so you could say that, but there's no point sending it unless you know where to go to. And the destination IP address tells the router where to send the data to. It gives an idea of where it's located in the world, and every router it goes via kind of takes it closer to that destination. What else could we say? We could say, the protocol being used. We could say it might have something called a checksum. A checksum is not, I don't think, directly on the spec, but it's good to know about. A checksum essentially will, in a sense, add up all of the data, let's say, and produce a number, which won't be 25, it will be a long number usually. And essentially this is added up again, or recalculated at least when the data arrives. And if the number produces different to the number given in the packet, well, there must have been an error when it was transmitted, and so it gets resent. So in essence, the checksum is a calculation done at both ends to see if the packet was corrupted or not. And that'll be usually in the footer of the packet, not that it really matters where it is. Now, the transport layer of network protocols splits data into packets before sending it. All the packets are received correctly. Good. Because if they weren't received correctly, it would have to figure out which ones didn't arrive, and it would have to retransmit or request it to be retransmitted. But we're going to assume they all arrived properly. So all the checksums were the same, for example, and there weren't any missing. Describe a process that ensures the data received matches the original. So really, I kind of said this already about the sequence number. The idea is you look at the sequence number and combine these so that the sequence run is in order. So let's say each packet sequence number is looked at and they are arranged so that the sequence is, how do we phrase this? And they're arranged so that all of the numbers are back in order, back in the original order. So this is really testing you on whether you know about sequence numbers, first of all, but also do you understand the fact that actually packets go via different routes. So once you send your data, all these little packets are going possibly different routes, possibly some get corrupted or some get slowed down by congestion. They don't always arrive in the same order they were sent out. In fact, rarely they'll do that. And so the packet number or sequence number is there to help rearrange it back to how it should be. 40, we need to construct another expression to show how many seconds it will take to transmit 20 megabytes of data using a network transmission speed of 2 megabits per second. And we're not calculating. First thing I do here is highlight the terms. So we're looking for how many seconds. We've got 20 megabytes, and we've got 2 megabits per second. Now, unlike the conversions from earlier, we're kind of awkwardly converting between two separate units. They're on two separate scales, or at least it seems that way. So what I always start with is thinking about my equation. I've got these three terms, how do they relate? Because while they seem like they don't relate, especially the two bottom ones, they obviously do. So bits per second, that's what BPS means, bits per second. Well, when we say that, what that means is we've got bits divided by the number of seconds. Right, that's what it means. Per means divided by, miles per hour, bits per seconds. So therefore, 2 megabits per second equals bits per second. Bits divided by seconds. Well, in terms of my other two terms, I have got bits. I'm told I've got 20 megabytes, and so I can fill that in. That's not bits, and so I'm going to have to convert it to be bits, and I've got to convert megabits per second to be bits per second here as well. So I might highlight that to remind myself that I'm not done with this bit yet. But then I've got seconds, which is my missing term. And now algebraically I can solve to find seconds because I've only got one term missing. Well, how am I going to get seconds on its own? Well, I can just swap 2 megabits per second with seconds. Right, so in effect, I'm looking for seconds. And now I've got 20 megabytes over 2 megabits per second. But like I say, we're not done because they're not in, we want both to be bits, effectively, both in terms of bits. Well, let's start with megabytes. As we said earlier, to go from megabytes all the way down to bits, we've got kilobytes in between. Then we've got, we've got bytes, of course. Then we've got bits. So we're going from big to small, so therefore we're timesing here. So times by 1024, times by 1024, and then I'm losing track of where I am, times by 8. Okay, so really the top bit of my fraction here is going to be 20 times 1024 squared, I could do to combine those two together, then times by 8. Right, so I've got 20, which is what was given in my question, and then I'm doing times 8 times 1024 twice to get that into bits. Now the bottom part, I need to get megabits per second into bits per second. Well, mega as a prefix is a million, so you could just write in a million, but then you've got, we could again just do, well, megabits per second is going to kilobits per second, and then bits per second. We haven't got times 8 at this point because it's in terms of bits already, it's not in terms of bytes. And confusingly, and it's just something you've got to know, unfortunately, confusingly, Edexcel have decided This time, it's in terms of 1,000, not 1,024. Now, I understand why they've done this. Personally, if I was the person writing the specification, I would not have made that choice, but whoever did made it for understandable reasons, because that's how sort of real life tends to work. But anyway, we're going in terms of 1,000, but like I say, 1,000 times 1,000 is 1,000,000. So really, I've got down here, let's do it in blue, 2 times 1,000 squared, which like I say is 1,000,000. And that should be it. So, a bit of faff to get to that point. I think as long as you're kind of happy or content with the fact that the equation is always the data you're sending divided by the seconds it's going to take equals bits per second. The key bit is rearranging it to get your missing term, but also the key bit is to make sure you've converted these two separate scales almost to be both in terms of bits. So in the case of the amount of data, this is in terms of 1,024, and don't forget the 8 as well to go from bytes to bits. And on the transmission speed, this is in terms of 1,000, and this time you do forget the 8 because we're always doing it in terms of bits. Now, because I've done quite a lot of working out here, I would always box my answer just to be clear what I'm wanting the examiner to look at. Issues and impact is up next in this sample paper, and this is a general topic which, a bit like networking, is quite short but has a lot in there. I tend to think that a lot of students don't really revise issues and impacts because they think, well, I can wing it. But actually, if you look at the spec, there are quite a lot of key terms you've got to know and specific things you've got to be aware of going into any exam. So we'll see what this particular question is like, but bear in mind for your actual exam, you could well get just knowledge questions which need quite a lot of revision. But having said that, the first question looks to be one which maybe you could wing to an extent. We've got to just state 2 environmental issues associated with the disposal of digital technology. So disposal being the key word here, it's not just any environmental impacts. Disposal is all about throwing stuff away once you've used it. Well, if it's not recycled, which often hardware isn't recycled, it'll just get sent to landfill and get buried under soil and with all the other rubbish. I was going to suggest as a second reason, maybe we could talk about the fact that in devices, small amounts of rare materials are used, which if you're just chucking it away, get lost. But to be honest, once you've got the device, disposing it isn't the cause of that problem. The cause is more for manufacturing. So you've almost got to kind of separate these issues into things like manufacturing, disposal, maintenance, etc. So I think one which is linked to disposal, and to be honest, manufacturing too, is about transport and the fact that moving stuff around is going to produce carbon emissions and produce, that will have a negative environmental impact. So let's say often, let's say recycling happens overseas, or just disposal happens overseas, which will usually require non-renewable fuels. Picturing those, massive cargo ships which take all the devices from the point of manufacture and then often will take them kind of back to whether get recycled or get disposed. They don't use, batteries. They've got loads of diesel engines. Not very good for the environment, which usually use non-renewable fuels. Okay, and now we've got a notification being shown on a computer screen. Thank you for clicking the link. Your important files are no longer accessible. Can you get access? Yes, just pay this Bitcoin address. The type of malware used in this attack would be ransomware. Ransomware is where the attacker holds you to ransom, demands payment in order to release your files. Often in Bitcoin because it can't be traced nearly as easily as, say, a bank transfer. Now we need to explain one way that digital systems may become vulnerable to cyber attacks when users do not properly maintain their software. So it's about users, not about developers. Well, how can a user not maintain their software? Maintenance is about kind of looking after stuff as an ongoing process once you've got it. Well, one big way is users not updating their software. It's an explain question, so we've got to say why this is a problem. Well, the problem is if there are bugs in the software, a patch may have been released. A patch is a particular type of update which fixes these bugs. And this may be enough for 2 marks, but I always think try and over-explain it if you can. Well, why is this a problem? Why is this making it vulnerable? Well, without the patch, the bugs remain, and an attacker could exploit. An issue, one thing people don't always think about is if a patch is released, it's obviously a sign there are bugs. And sometimes even the developer will say, oh, we fixed this bug in X feature. And so an attacker can see that and has got knowledge where the bug is. And so they can start to exploit it, start to target people who have not updated their software. Okay, and now part C, people use spoken commands to interact with digital assistants, things like Siri and Alexa. Explain one ethical concern associated with digital assistant technologies. What ethics are about what we think is right or wrong, not always about laws, it's more about individual people. Well, I would say a big issue with these digital assistants is privacy. The idea that, first of all, it's listening to your voice and recording your voice, and you're not quite sure to what extent that's being stored by the company. Presumably they are storing a lot of it to train the AI to be better. But then again, I would say a lot of things which put people off is the fact that it could be always recording you. To be able to pick up on things like Hey Siri and so on, it will be to an extent listening permanently. So we could say privacy can be a concern since it's not always clear when the device is listening or not. And again, to make a second point, to be super clear, we are getting 2 marks here. Users might be concerned that it's listening in on private conversations. Might be concerned that workers are listening in on private conversations. With ethics, there are usually quite a wide range of things you could say. I would just always stick to fairly safe areas like privacy. I wouldn't try and get too controversial, or in the case of this, like too conspiracy laden. I would keep things fairly simple. And part D in this ethics, in this impacts section, is about acceptable use policies. So students are asked to sign one of these, explain one way that an acceptable use policy helps to protect student data. So you probably signed one of these, or your parents did at some point when you joined your school. And my school, it's done, I think, in year 6. It's not a very robust policy, unfortunately. It's not up to me. So the point of this is, this policy says or outlines all of the things you are expected or you are allowed to do on the computers on the network. But it should also say all the things you're not allowed to do. So you can't go on certain websites, you can't maybe install malware, you can't log in from home. Those could all be in these policies. And crucially, it should also say what the consequences are. So if you are banned from using USB sticks, but you plug one in to put a game on your computer, what is the consequence of that? That's what they should say. In reality, they don't always have that clarity, but that's how they are used in industry, or are meant to be used in industry. So how can it actually protect student data? Well, not directly, of course, but how can it improve things? Well, if it's very clear what the consequences of misuse are, then it might act as a deterrent. It might put people off misusing a computer and so putting data at risk. So I've gone down the kind of people deliberately wanting to misuse the computer route here by saying, well, if it's saying what consequences there are, ideally it might put people off, it might deter people from doing things which could put data at risk. So for example, it might deter people from going on random dodgy websites which could download malware, say, and you might give that example if you had time to add that at the bottom. So it's not always malicious, it can just be used as a training tool to try and increase the awareness of people using the computers. Now starting the computers topic, we are looking at starting the computer subtopic. So one function of utility software is to provide anti-malware state to other functions of utility software. So utilities are there to help us run our computer system. They sort of do housekeeping jobs, you could say. Jobs which, if we didn't have a computer, you wouldn't need. So anti-malware, which finds and removes malware. If we didn't have a computer, we wouldn't need that as a concept, right? Whereas something like a word processor, well, if we didn't have a computer, we'd still be writing documents, so therefore that's not utility. Now it's a slightly weird, it's a slightly odd way of phrasing this question, because they're not really functions, they're separate bits of software. So essentially, what other utilities do we have? Well, we have defragmentation software. This works on magnetic hard drives, it's not really needed on SSDs. And what it does is it rearranges the disk so that your files are not dotted about across the disk surface. Ideally, they're all stored in one rough area so that it's quicker to access. And so defragmentation software kind of moves it so it's in one region. Another example would be, first one which comes to my head is compression. So compression software will make file sizes smaller in order to speed up transfer times and also to take up less space on a storage device. We also have things like backups and repair software, which are the two other ones also on this spec. Now, to state one way that a code review helps programmers to produce robust software. So if software is robust, it won't break easily. It means if you type in a dodgy input, it won't suddenly crash. It means that it'll be stable over time. A code review is either done in person by a human or it's done by a tool. What it does is look through the code and try and find usually things like bugs and general weaknesses in the code, but also just sort of bad programming practice. So the tools in particular can spot well-known vulnerabilities. A human might spot, inappropriate use of global variables or a badly defined subroutine or something like that. So okay, let's stick to the kind of bugs aspect. So it might identify any security vulnerabilities, and that doesn't really say why it helps. Well, so that they can be fixed. Equally, it could be the developer is getting some advice on how to program in a more appropriate style, perhaps. Okay, a full marker here. We've got to describe the role of the control unit, the control bus, the data bus, and the address bus when fetching an instruction from memory. Okay, so we've got our memory, which is usually RAM, but could be cache, it could be ROM as well. We've got our CPU, and the CPU has got the control unit in it. We've also got the ALU, and we've got registers, and also a little bit of cache usually too, but that's not listed in the question. Now, connecting up these devices, we have these three buses. So a bus is just a wire in essence. Now, a control bus is bidirectional, so data can travel both ways down it, so data is moving backwards and forwards. The control bus, as we'll say in a second, is there to send signals to control the hardware. So the control unit will really be attached to this control bus and will send requests via this control bus. The second type of bus is, let's do the data bus next. The data bus is also bidirectional, goes both ways. So this is where the actual instruction is going to go through. Now, we do have a distinction in this topic between instructions and data. In this case, the instruction is going down the data bus a little bit unhelpfully. It won't go down the control bus because that's just for kind of signals overseeing the process. And it won't go down the address bus because the address bus is just where the data, or where the instruction in this case, is coming from. Now, the address bus is, maybe not too blue. The address bus is not bidirectional. This is unidirectional, which means data only travels towards the memory. Nothing goes back to the CPU via the address bus. Anything which goes back will go via the data bus, or if it's a kind of more general message, it will go via the control bus. So as lovely as this diagram is, this does not get us any marks. So let's say goodbye to it. How can we start this process? Let's start with a mention of what the control unit does. So the control unit really oversees everything in the CPU, quite frankly. So we're going to start with the control unit. We'll start the fetch operation. And it will use the control bus to let the memory know that it wants to receive data. And we'll place a read request on the control bus. Now, the way this would typically work is, each bus is a series of parallel wires. Let's just pretend these are parallel lines. Now, if it is, say, a 64-bit computer, it'll have 64 wires typically. So loads. But just as a kind of basic level, each wire will represent a particular message. So one will be like for reading, one will be for writing, one will be for something called interrupts, where the CPU stops what it's doing because something more important is happening. One will be for the clock, so a clock signal will go via this control bus, etc. I can't think of all 64 in this area, not that you'll need all of them necessarily. Right, so what's happening effectively at this stage is, right, we're about to fetch, control unit sends a message alongside the read line of this bus to let the memory know that it's about to read, so that it can get set up. Whereas if it sent a write request, obviously it would be about to write data to it. But otherwise, the process is not different if you're reading and writing from this point onwards. The difference is just between what the control bus is informing the memory is happening. So once this is done, the next step is going to be, what was I saying earlier? The next step is going to be to place the address of this instruction on the address bus. Maybe we won't use the word address. Let's say the location of the instruction in memory is then sent along the address bus. The memory will get this address, and because it knows we're reading because of the message along the control bus, it will send this data back. It will send the data back. The memory will send this instruction to the CPU via the data bus. So there's no such thing as an instruction bus, it's always done down the data bus. And maybe I can be a little bit more clear about what would happen if it was the other way around. If we were writing data to memory, which could well be a question, of course, very similar answer to this one, except we're placing a write request on the control bus. It will send the location. This time it will be the location of where it wants to save this, whatever it is, this data. And then it'll be the CPU which puts the actual data on the data bus, not the memory. So it's just going the other way if we're writing to memory, but ultimately it's a similar process. And I realise, I think maybe I was talking over it. I've written instruction twice there. The data bus is what that should be. Then we have a question on the operating system. So the operating system controls the scheduling of processes. Describe how the OS uses scheduling to allocate processor time for 4 marks. It's definitely one of the harder questions on the paper so far. This wouldn't be out of place in an A-level paper actually, but still, there's got to be questions aimed at the top in GCSE 2. So the operating system is our software which really manages both our applications and the hardware. So in this case, it's all about how does the OS manage the processor. But specifically, how does it schedule our processes? So a program is made up of many instructions. These will correspond to processes, and a process will be something the CPU has got to do. It will be more than one instruction. Usually a process might be a fair few instructions, and then it will switch to a different program. So how does it use scheduling? Well, scheduling is all about what happens when, right? So the idea is, in memory, there'll be several processes waiting to be executed, and the CPU will decide, first of all, the order of this, and it'll be ranked based on their priorities. So how important are they? What is their priority? So certain things are, more important than others. For example, me drawing on this graphics tablet, every time I touch it, that needs to get dealt with straight away, that can't be delayed. Whereas a background refresh of Spotify, which I've got open, is less important and so would have a lower priority, you would suspect. So not only does it kind of assign priorities and the order in which it should be executed, also it will decide how long it should take. So maybe this might be 5 cycles, CPU cycles, this might be 10 cycles, this might be 30 cycles, this might be 2 cycles. So it'll depend on, first of all, how important it is. I don't know if I've really corresponded that to importance there, but also about how much that process needs. Some processes are quite simple for the CPU, others will require lots of repeats of the fetch execute cycle. So it's both in terms of priorities, but also the time allocated, and the formal term for this is the time slice. So how much time is allocated where that process has got access to the CPU. So let's start by saying the OS will allocate priorities to processes in memory. And we could just clarify this a little bit, maybe to say more time critical processes will be given higher priorities, meaning they'll get executed sooner. And we can also say the length of time given to each process is allocated by the CPU. And this is the time slice. Now, this is not necessarily how long that process needs. Process 1 might need 5 clock cycles, but initially it gets 2, then it gets 3 later on. So the CPU won't just, adhere to what the process wants. It's going to break it down further if it needs to, and will just switch in and out of your processes. So we can say when a process's time slice finishes, the next highest priority process is executed. And maybe to be sure that we're getting all 4 marks, so we can say something along the lines of the previous process, if it is unfinished, will be executed at a later point. Because, like I say, often it won't finish, it will just be a bit of it, something else, a bit of it again, something else. It will switch backwards and forwards if it is unfinished. And it's not really asking about it here, but generally as a principle, the OS will rapidly switch backwards and forwards between different processes so that everything gets executed and it behaves like it's doing it in parallel, which it's not always. Okay, so tricky this one, quite possibly a fair few people wouldn't get 4 marks here, which is not anything to worry too much about. Of course, we want to try and aim for 4 marks, especially if you're aiming for the top grades. But I think he could quite easily, well not easily, you could quite possibly get a few of these marks at least, even if all 4 is trickier than some other 4 markers we might come across. Okay, and we've now got a 6 marker. There's usually going to be one of these, or there should be one, there will be one of these. So a team of programmers is creating a code for an alarm system. The system uses a high-level programming language for the touchscreen graphical user interface and low-level language for the control unit that monitors the sensors and triggers the alarm. Okay, so what's worth highlighting here? We've got high level, which is for the GUI, okay? So what's seen by the user, and low level for the control unit, which is probably an embedded system, would be my assumption. Embedded system being a very small and dedicated system to one job. We need to discuss the characteristics of high-level languages and low-level languages that make them appropriate for the team of programmers to code these uses. So it should consider the purpose of the system, which what that's saying is link it to the scenario, and the just general advantages of both of these. So this is not asking us to disagree with this choice. They're kind of suggesting this choice is fair enough. Well, why is it fair enough? So high-level languages are very abstracted from how a CPU actually works. Python is a high-level language. We're going something like, do code like while age is bigger than 30, whatever it is, right? Despite it not being clearly pure written English, we make use of English terms, and it's meant to be fairly readable and fairly easy to write and understand. And Python, as a particular high-level language, is very high-level. There are other high-level languages which are a little bit more, or a little bit less abstract. Something like C is less readable than Python, for example. Low-level languages are either machine code or assembly code. Assembly code is probably what they're using, because machine code is just binary. Assembly code is something like add register 1 to register 2, or maybe move 5 to register 6, whatever. Very short commands like these, which make use of some bits of English and some mnemonics, some shorthand, but less readable, less easy to use. Personally, I did not particularly enjoy my time coding in assembly. It is tricky to use, but it does have advantages. So you might do a little quick plan before you start this. These questions are not assessing you on spelling and grammar, but they are looking for a coherent discussion of these. They are looking for a rough order. Now, often the bullet points will be the order you take this in. The purpose of the system, I think, is just going to feed into our advantages here. There's no need to address this one by one, I would suggest. Well, let's leave assembly for now. What are the benefits of a high-level language? Well, you might want to think, well, they're readable. It's easy for the team to use. I would say they're popular. What I found when I was doing assembly language coding was it was very hard to find stuff. We know that if you've got a bug in Python, you just Google it and you've got loads of responses. Assembly code tends to be specific to the particular embedded system, and so there are so many different types of assembly that getting help is less easy. So because it's popular, easier to get help, and also recruitment, you can hire new people more easily. Putting an advert out for a particular niche assembly language might be difficult to get many applicants. So more so could say like finding errors, it's easier to find errors. Those could be our kind of 3 points for high level. And what about low level? Well, I would suggest, I mentioned it's probably an embedded system. So because it's specific, if you've got a very specific embedded system, you might not really have a choice to do a high level language. If it is a kind of knockoff version you found from a obscure supplier, it might not be compatible with high level languages because there might not be a translator which can translate to its machine code. So you might have to use it because of how specific your system is. Also, another benefit is you've got a lot more control. You are controlling things like registers, and so you've got more power, you've got more opportunity to control it how you want, and also it will be faster to execute. So if it's very simple hardware and very basic hardware, you want to maximize how fast it is. And to be honest, you could even argue, well, if it's an alarm system, you don't want any delay, although to be honest, the delay would be minuscule. So maybe I won't say that. I think it's 6 marks. 6 distinct points is a bit excessive. Probably looking for 4 or 5 which are explained and linked to a scenario. So let's see how we get on. I wouldn't spend the 3 minutes I've spent talking about this in the exam. I would just try and drop this down in 30 seconds, 45 seconds if you can, because otherwise it's going to eat into your time to actually answer it. So let's start with high level languages and say something along the lines of, compared to low level languages, high level languages are more readable. And linking it to the scenario, it said there's a team of programmers. What's the consequence of this might mean? Meaning the team is able to understand each other's code more easily. Errors in the code may be easier to fix. And we could try and link this into kind of popularity, especially because there is likely to be a lot of material online. And we could even, I finished the sentence, but we could even say because of the popularity of many of the languages. And I want to kind of mention recruitment here. We've got a bit of space. I wouldn't worry too much about how much space you've got, but it will guide you into how much you're writing. If you're easily filling up the space, it's a sign you've written a little bit too much. Because of the popularity of many of the languages, this therefore may also make further recruitment easier. That's probably enough for high level. You could maybe say more, like, I think in terms of the reasons, there are more reasons for high level because that's what we use most of the time, right? But low level languages like assembly do have their place. They are used. So what did I say in my plan? I said specific. So let's say the control unit might be part of an embedded system which has a very specific instruction set. Link this to a scenario and say something along the lines of, for the control unit may be part of an embedded system which has a very specific instruction set. An instruction set is the kind of set of machine code commands, and so therefore this could mean there is not a high level language or a translator which can work with it. So just for your context, if you're not following me at this point, if I have a command like for world, if I did in Python, this has to get translated to machine code, and on say an Intel CPU, this might be translated to 1101. Let's pretend. Whereas say an AMD CPU might be translated to say 1011. Say. So the actual machine code is different. And when you write Python code, if you run it on a Mac, if you run it on a Windows computer, if you run it on Intel, on AMD, the translator will make sure it goes to the correct machine code. But if it is a very obscure CPU made by a random company or based on a weird architecture, a normal translator doesn't know how to translate it. And so if you have that situation, you've kind of got to write it in low level, maybe even directly in machine code, because nothing else is able to put it in that machine code. Now that's rare, but for a simple embedded system, there might not be a translator from high level to low level. It might only be an assembler going from assembly code to machine code. Okay, what else did I say at this point? I mentioned the control. So one benefit might be my delay is, I'm thinking, is that really an advantage? I guess it kind of is. You haven't really got a choice, but it's still an advantage of it. But a clear advantage is, let's go back to red. An advantage is that you've got more control over the hardware. So thinking about this scenario, what could that mean? It could mean maybe you've got access to the sensors directly. You know, if you were writing Python code and you had a sensor plugged into your computer, would you know how to control it? I certainly wouldn't, but I know for a fact that in assembly code you could quite easily go to the pin it's plugged in and access it that way. It may be wise as good to tweak their sensitivity maybe. That's probably almost enough. You might manage to get 6 marks if the examiner was feeling kind, but let's mention the speed as well. Finally, because low-level languages do not have to be translated much and can be optimized, meaning they are very tailored to that specific machine code, it means they will execute faster. Now, I kind of went off my point earlier about the fact that with an alarm system, that delay wouldn't be helpful. It would be a tiny delay, but let's say that anyway. Any delay in the alarm system would be unhelpful. Okay, so hopefully you can see that I've tried to link these points together. It is a little bit tricky because we are kind of making separate points here. I'd say more to the point here that I've tried to link it to a scenario as best I can. Again, there aren't loads of areas to do this. I've kind of mentioned recruitment, so you've got the team. I've kind of mentioned that it might, in this particular case, be working on an embedded system, about the sensors, and about the alarm system. I've tried to mention it where I can. It's not, like I said, it's not always a perfect fit, but it is important to be getting the higher marks for these 6 markers. Don't always need to make six distinct points, which I've kind of done here. It's marked on the whole. So if your answer flows together well and makes sense in the context of the scenario, you might only need 4 or 5 points, but make sure they are hitting all of the bullet points given in the question. The last question in this paper is on computational thinking, which, I don't know, maybe I'm just pessimistic, but I suspect there'll be at least one person every year who rocks up to paper 1 and is surprised to see this in here, because this is where Edexcel are going to ask you questions about programming. Now, some of it is quite abstract, so stuff about algorithms is just another aspect of theory, you could argue, such as the different searching and sorting algorithms. But then some of it, as we'll see, I'm sure, are questions which have got code and relate to our understanding of code. So, as you hopefully know, paper 2 is pure programming. Write this code, amend this code. There's little room to test certain knowledge, and so they'll use this question to do this. My suspicion is it's always going to be a pretty big part of the paper, so 18 marks in this case. Now, if it does come up last, which it won't always, I suppose, you might want to try and give it as much time as you can, especially if it's not a strength of yours, potentially. So first question, we need to state the type of error that can be found in algorithms. Well, the fact that it says the type and algorithms in bold is meant to lead you towards one of our 3. So we've got logic errors, we've got syntax errors, and we've got runtime errors. Out of those 3, the ones which are in algorithms, you would suggest are logic errors. So a logic error is where the code, or whatever it is, the instruction works, but not as you would expect it to. A syntax error is an issue with the grammar of your language, so maybe you've misspelled a keyword. And a runtime error is where the code starts to run, but doesn't finish. It crashes mid-execution. Well, an algorithm is abstract meaning it's detached from any particular implementation, and so therefore there is no syntax and there is no runtime because it's just how to solve a certain problem. So only a logic error can occur in algorithms. Now, for 3 marks, we've got a binary search algorithm used with this list to find the target item, target value B. Zoom in a little bit. We need to complete the table to show the 3 characters in the order that the algorithm would compare them against the target value. So 4th comparison is to get B itself. Well, let's have a look at this. The way binary search works is it will start in the middle and keep dividing the list into, keep looking at the middle values until it finds your item, but crucially the direction it goes will try and eliminate letters in this case, which can't actually exist, so or can't contain our item. Because this is sorted, we can use binary search on it. If it wasn't sorted, you can eliminate the halves as you go. So the middle item, the middle letter here is going to be what? F. We've got 5 either side, yeah. So F is our first letter we're comparing it against. And because F is bigger than B alphabetically, we can eliminate F and the letters above it. The second comparison is going to be the middle of the next ones, which is going to be C. And because B is smaller than C, we can eliminate those. And now we've got A and B. Well, because it's an even number of items too, it's not a true middle. So you either pick the left side or the right side. Well, if our fourth comparison is for B, our third comparison is therefore going to be picking A as our next one, which is then eliminated, and we get B. So I guess the key of binary search is if there isn't a true middle, you pick either the left or right of that true middle. Just be consistent with your choice, but if it kind of leads you towards a particular choice, follow along with that as well. Now, programmers can use all capitals to show that a value is a constant. A constant is shown here on line 3, so max capacity is in capital letters. Explain one reason why programmers use signals indicating a value as a constant, rather than repeating the same fixed value throughout an algorithm. Goodness knows what they think that means. Don't know what they mean by that. That could be a typo from symbols, potentially. Don't know. I don't think that's the correct use of that word. But anyway, the question is valid. Especially in Python, in Python, there are no true constants. In some languages, you can write down something like const pi equals 3.14, and it will be a constant, and you just cannot change it later on. You'll get an error. We don't have true constants like those in Python, so instead it's more of a kind of annotation than anything most of the time. But actually, it's useful for the case mentioned here. So the idea being a constant you can set at the top of your code, and it will apply all the way down your code. So that if you decide to change the constant later on, the capacity of this pool goes up some, you don't have to change every single instance of that value later on. If you had 120 listed in loads of different areas of your program and it changed, well, that's a pain to change. Best to change it once at the top. So let's say, so that it is easier to change if a constant value needs to be updated. That's more of us stating it. So why is this the case? Why is that true? Well, this is because initializing a constant means that only that initial assignment needs to be changed, and it will apply throughout your code. This isn't the only reason, to be clear. It's I think the most obvious one based on the wording of this question, but readability helps. You know what max capacity is. Just 120 throughout your entire program. Well, what does that mean? You don't know what that is without the context. It makes it more readable. It's almost like a comment, really. And also, less likely to be changed by mistake. Like I said, in Python, it's more symbolic. It's more of a annotation. Well, if it's in capital letters, your teammate who's just joined your programming team will know not to fiddle with it because it's marked as a constant. So it's less likely there'll be accidental changes to the constants. Right, we've got Margaret now owning an ice cream shop. It's currently baking at the moment as I record it, so that's making me a bit jealous. The program manipulates sales figures from Margaret's shop, and we've got Python code here. Like I say, paper 1 you will be given some Python code. You can't just switch off your Python brain for paper 1. We've got a few variables initialized at the top. We've got a text file being used, for loop, if statements, and that's it. We've got a final print at the end. I tend to think with trace tables, as we have here, people often forget any final prints, I've noticed. Now, the only inputs from a file to the program are these 4 numbers. So we don't actually see the file, but we assume it's got these 4 lines in. We're going to complete a trace table to show these changes of these 4 inputs. So display is what's getting printed. It's not actually a variable in the code. Now let me just fiddle with this so I can get it all on one screen. Hopefully this will be big enough to see. So the trace table is there to show how things change as we execute a program. It's often good for finding logic errors, at least in theory. And the key idea is only write down a value when it's changed for one of your 4 columns. And step through it line by line. Some people like to try and show off and just take in the code, write down what's happening, and 9 times out of 10 they're wrong because there's a little tweak they haven't noticed. So don't try and be too clever and figure out what's going on. Just take it line by line and make sure you understand, or make sure you're following every single line. So, line 2. Was there line 0? No. Line 2. So num is set to 0. I write it in. X is set to 999. Now you could put that there instead. I always like to, my logic with trace tables is, if it's in the same block of code, I'll generally put it on the same line. The order of these 4 lines makes no difference, and so having it in a nice diagonal line just doesn't make sense to me. Not every row of a trace table is meant to be a line. That's not how they need to correspond. So if you've got enough space, you could do that. I just think it's a little bit unnecessary. Y is set to 0, and line is not one of our 4, so we ignore it. We open the file, and so we've got these 4 numbers loaded in, we assume, and 4 line in F. Again, line is not one of my 4, but we start with 355, which we have to assume, based on this information, is our first line. So now num is set to be the integer version of 355, so num is set to 355. So it'll be a string when it comes in. I should have really put those quotes, but now it's an integer. So now if num is less than x, well x is 999, and it is less than that, so now x is set to num. Again, you could do it below, but I'm personally not going to. Then, because it's an if statement and not an elif statement, we don't skip that second one. If that was elif, we'd move on, but because they're separate if statements, we've got to check those. If num is greater than y, well 355 is bigger than y, and so y is set to num as well. Nothing's been displayed yet, nothing's been printed, so we loop back round. Our second line is 554, and so we set num to be 554. If num is less than x, which it's not, so we don't change x, but num is bigger than y, and so y is now set to be num. Based on where I'm doing it, I've now got a gap under x, which is perfectly fine. We're going to have loads of gaps in most trace tables. We loop back round. Our next number, I'll start to erase these, our next number is 199. So that's what num is set to, 199. If num is less than x, which it is, so we're going to set x to be 199. Now, this is where the gap is quite important, I would suggest. You might still get a mark if you put 199 in that gap, but trace table was meant to show how it progresses over time. So really, this has happened way after we set num to be 554, and so it should come afterwards, in my opinion. If num is greater than y, which is not, so no y is left as it is, we loop back round, and we're on our final line, 409. Num is set to 409. And if num is less than x, which it's not, if num is bigger than y, which it's not, they remain as they are. And now we're going to print x and y, because our for loop is done. We've finished these 4 lines of the file we've got to assume. So we go to line 14 and print x and y, that's what goes to display. We're going to print 199, and we're going to print 554. In Python, having a comma like this will give it a space. So I've put that a line after 409 because again, I'm kind of picturing this for loop's finished. I'm now on my next block of code, which is on its own line. And that should be it. Now, I don't know if we're going to get a follow-up question about what this is. We are not. Sometimes it'll ask you afterwards, state the purpose of this code. In this particular case, as you may figure out, it's finding the smallest item in this file and also the biggest item in this file. That's what it should be doing, and we can see that actually that's what it has done. If you kind of spot the pattern and then the code doesn't seem to work and there are no questions about logic errors, you might have made a mistake in the trace table. So in essence, don't be afraid to leave gaps, take it line by line, don't jump ahead. If you figured out it was doing smallest and biggest midway through, don't skip ahead, still go through every line one at a time. Now trace tables, some people hate them, I do understand that. I've got a very long video with lots of practice questions on trace tables. If you want to have a look at that, just search trace tables on my channel. Right, moving on, and this is our last question, which is nice, a big flowchart. We told customers can get a voucher for their favourite item. Customers whose favourite item is cookies get a voucher for cookies, and customers who do not choose either get a voucher for drinks. Or do not choose either, okay. We're completing the flowchart to show this process for 6 marks, so we've obviously got a fair bit to fill in. Only 3 obvious gaps in this flowchart. Our first gap is a parallelogram, which are for either input or output. You can see we've got 2 prints for output on the right hand side. Well, in our diamond, which is for a decision, we've got choice equals ice cream, so therefore choice has been gained from the user, and so let's just ask the user for their choice, just input choice. Now there is not one set way to do flowcharts. This is fairly code-like, but it's obviously not totally Python code, so how you do it could vary a tiny bit. Maybe I'll try and do that as a capital C in case they're using choice as a bit of a variable. So choice equals ice cream, they're going to print ice cream voucher, which makes sense. They get ice cream voucher if their favourite item is a ice cream. But if it's not, we're going to give them a voucher for cookies if their favourite item is cookies. But we can't just jump ahead. We can't just connect up this arrow to the cookie voucher, because they could type in nothing and we'll still get a cookie voucher. It's only if their favourite item is cookies. So let's just replicate this selection block with a choice for cookies. Try and do this as neat as I can. After a long video, this gets worse and worse. Okay, not my worst. If their choice equals cookies, if it's yes, make sure you write in yes. We're going to print cookie voucher. Otherwise, we're going to get a voucher for drinks. Now we haven't got a voucher spot. This last box should really be for end. When we finish our algorithm, we've got a start symbol at the start, and we should have an end one as well. Okay, or drawing is bad. We've got a bit of space here, so we've got to also print a voucher for drinks if it was no to both of these questions. So let's do that. This is for no. We're going to print drinks voucher as a parallelogram. Dear oh dear. Okay, fine. Does the job, I would say. That seems to be it. We can double check just by checking the scenario, but that should be us for this question. I think a lot of students are conditioned to find the last question the hardest. A lot of exam boards set up this way. Edexcel won't do that necessarily because they do the different topic breakdowns, but you may well get a pseudocode question alternatively at the endpoint. You've got to know this programming knowledge, and I've done practice of things like trace tables and these kind of algorithm questions, otherwise you'll get caught out potentially in paper 1 and not just in paper 2. Now at this point, ideally you've got 10-15 minutes spare, and you shouldn't be sat there relaxing thinking about your next exam. You should be going back through and checking every single word you wrote, ideally, because there will be mistakes and you may, for certain questions, have some new ideas once you get to this point. Be careful not to ruin your answers by adding loads more content. You see sometimes someone writing a page for a 4 marker just because they had time and wanted to cram in stuff. It rarely helps that much. But if you can pad out or boost a few answers, especially the longer mark ones, that would be great. So hopefully this video was helpful. Well done if you managed to watch a big chunk of it. I really hope if you have this exam soon, it goes really well, and best of luck.